Assalamu alaikum everyone. I am going to review the electric circuit analysis. So there are 5 basic elements of the electric circuits analysis. These are voltage source, current source, resistor, inductor and capacitor. So first one is the voltage source. A voltage source is a two-terminal circuit element that maintains a voltage across its terminal. The value of the voltage is the defined characteristic of a voltage source. Voltage source always replaced by a jumper to a specified circuit. So the second one is the current source. A current source is a two-terminal circuit element that maintains a current through its terminal. The value of the current is the defining characteristic of a current source. Any current source is replaced with an open circuit when specifying a circuit. Third one is resistor. A resistor is a two-terminal circuit element that has a constant ratio of the voltage across its terminal to the current through its terminals. The value of the ratio of the voltage to a current is the defining characteristic of the resistor. So fourth one is inductor. An inductor is a coil of wire through which electrons move and energy is stored in the resulting magnetic field. Inductors are simply coils of wire. The wire can be air wound just in the middle of the coil. A wire be wound around a permeable material that concentrate magnetic fields. A wire wound around a circular form. Inductor is measured in henries. Henries is the units of the inductor. So the last one and the fifth one is the capacitors. A device that stores energy in the electric field are known as capacitors. Two conductive plates separated by a non-conductive material. Think of a capacitor as very small temporary storage battery. The unit of capacitors are farad. Now we have Ohm's law. Ohm's law states that the current through a conductor between the 2 points is directly proportional to the difference across the 2 points and inversely proportional to the resistors between them. The mathematical equation that describes this relation is V is equal to IR. Now we have Kirchhoff's current law, that means KCL. KCL states that the sum of the current entering a node will be equal to the sum of the current leaving a node. Here we can see a circuit that explains KCL. So we have IT means total current is equal to IR1 resistor 1 current of resistor 1 plus current of resistor 2 plus current of resistor 3 and up to so on. So then we put values of the current. So then we put value of the currents, we can find that KCL. So here we have two different circuits. So here we have two circuits. This circuit shows when the resistors are in parallel, the current may divide. And the second circuit shows when resistors are in series, the current may not divide. Voltage may not divide. So here we have another two circuits. In these circuits we can see that there are two resistors in parallel and one in series. So this is the equation of these resistors. The total current is equal to the current of the resistor 1, 2, 3 and up to so on. So here we have two resistors. So we can see the way here we have two resistors, resistor 1 and resistor 2. So the total resistor is 11 mA. milliampere, and resistor 1 and resistor 2. Resistor 1 is 1 milliampere, while resistor 2 we have to find. So the total resistor R2 becomes 10 milliampere. Here we have Kirchhoff's voltage law, KVL. This law states that this law is also known as Kirchhoff's loop's rule, is a result of the electrostatic field being conservative. It states that the total voltage around a closed loop must be equal to 0. Here we can see an example of the KVL. KVL states that the sum of the voltage drops around a closed loop will equal the applied voltage. Here we see a circuits to explaining the KVL. The total voltage is equal to voltage of resistor 1 plus voltage of resistor 2 plus voltage of resistor 3 and up to so on, as in the case of KCL, Kirchhoff current law. So the voltage become 12. Total voltage become 12, and the sum of resistor 1, resistor 2 and resistor 3 voltage also become 12, which proves KVL. KVL can be used to solve for an unknown voltage drop. Here we can see another example which also proves the KVL. The total voltage is equal to the voltage of resistor 1 plus voltage of resistor 2 plus voltage of resistor 3 and up to so on. The total voltage is 10 volt and resistor 1 and 2 are 3 and 2, while we have to find voltage of resistor 3. Here we apply KVL on this circuit to find the voltage of resistor 3. So the voltage of resistor 3 become voltage of total voltage minus voltage of resistor 1 plus voltage of resistor 2, which is 3 plus 2. So we can find the voltage of resistor 3 by applying KVL. Now we have Thevenin's theorem. Through the use of the Thevenin theorem, we have the ability to reduce a complex circuit down to a simple series circuit. There are 4 steps to apply Thevenin's theorem. First step is to remove the load. Second step is to determine the voltage seen by the load V Thevenin, which means V Thevenin. VTH means V Thevenin. Third, we replace the voltage source with a short. Do not short out the power supply. There is a difference. And finally, we determine the resistor seen by the load. RTH means R Thevenin. These are the steps. First steps, we remove the load. As we can see, R load 1 minus 1 kilo ohms is the R load. We can remove the R load. Second, we determine the voltage seen by the VTH. Third, voltage with the short. We short circuit the voltage. Determine the seen by the voltage V Thevenin. Since R3 and R4 are not connected on the end, they do not carry current. Therefore, they cannot have voltage drop. The voltage present between point A and B is the drop across R2, as we can see in this circuit. Here we apply the voltage divider, where R2 is 4 and VTH is 4 ampere. While we put the values of the resistor 1, 2 and 5 and the total voltage, we can find the voltage by voltage divider. Fourth step, determine the resistor seen by the load resistor. Here we see the circuit. So the two resistors are in parallel. Resistor 3, resistor 1 and resistor 5 are in series, while they are in parallel with resistor 2, and the equivalent of all the resistors are in series with resistor 4. So we can apply series and equivalent resistor combinations, and we can solve the RTH. We can find RTH. which means R-Thevenin. Here we have Norton's theorem. By reducing all the elements of a complex circuit to a single current source and a single source resistance which supply power to a load, a simple circuit can be created. So here we can see Norton's theorem. I node means I Norton and R node means resistor Norton. Norton resistance and Norton current. Here we have the steps to apply Norton's theorem. First is to remove the load like Thevenin's theorem. Second, determine the seen current by the load. Third is to short the circuit power supply. Fourth one, determine the resistance by a seen load. So here is the equivalent Norton circuit. By applying these steps, we can find Norton's circuits equivalents. So it is the last topic. So thank you.